So thanks again for joining. And then I strongly encourage you to keep your video on so that we can have this usual seminar atmosphere throughout. And then this talk is being recorded. The recording has just begun, but the coffee break is not recorded. And also, I encourage you to keep your video on, but your video will not be captured until you ask a question or you speak up. And speaking about the questions, you can ask questions by either sending a private message to me via the chat feature, or by clicking the raise hand option that you can see. And then if you raise your hand virtually, then I will handle your questions. Questions are, of course, very much welcome during the talk and also after the talk. And if there's any problem or concern, then you can send a private message to me so that I can handle as a host, the chair of this session. So that is it as a general announcement. So we can now move on to the talk part. So if Justine, you can start sharing your screen, that would be great.
I will do that.
Great. So let's move on to the talk. Today we have Justine Seu from University of Wisconsin-Madison, and he will talk about a probabilistic separation logic. Please start.
Hello, everyone. Thanks a lot for the organizers for putting on this event. I've watched several of the videos before, and I'm really happy to be speaking to all of you all today. Like Coco mentioned, I'm going to be talking about some recent work on a probabilistic separation logic. There are many things that this might mean, and I hope to convince you that at least what we did is a kind of a reasonable approach to the kind of designing such a logic. So before I start, I should say that this is joint work with a bunch of brilliant collaborators, Gilles Bart and Kevin Liao, and more recently, Jialu Bao, who is at Wisconsin also, Simon Doherty, and Alexander Silva. Okay, so definitely feel free to stop me at any time. I'm not intent on getting through all of these slides, and I'm happy for any kind of questions. So let's start with independence or probabilistic independence. So what does this mean intuitively? So we typically think of kind of two random variables, X and Y, are independent if they're uncorrelated. So if you think of observing the value of one of these variables, say X, then you're given no new information about the value or the distribution of Y. So if you imagine I have kind of two unknown quantities, and then someone tells me that X is actually equal to true, this should not change my belief or my best guess at what the value or distribution of the other variable is. Okay, so this is kind of an intuitive explanation. For some examples, things that are independent, the most typical one, at least in say program verification or in the setting of probabilistic programs, which is mostly what I'm going to be talking about today, things that are independent come from fresh random samples. So if X is the result of one fair coin flip, and then the Y is the result of another kind of quote unquote fresh coin flip, then X and Y are going to be independent or probabilistic independent. So more generally, independent things come from somehow separate sources of randomness. So I have a bunch of coin flips here that I've made and I calculate something with them. And then I have another bunch of fresh coin flips over here and I calculate something else with them. And the two results of what I've calculated should be independent. At least that's the general intuition. More generally, kind of beyond probabilistic programs, kind of uncorrelated things are often thought of as independent. So if I think of modeling, maybe X is today's winning lottery number. I don't know what it is yet because it hasn't been published. Maybe I have some distribution or belief about what this thing should be. And maybe Y is kind of the closing price of the stock market today. Again, I don't kind of know what the closing price is, and I maybe have some distribution or belief about what this thing should be. Then intuitively, I might expect that X and Y are uncorrelated, and therefore they should be modeled as independent random variables. So this is another example of kind of things that, intuitively maybe have no relation between each other. This is kind of a modeling choice. So, if I'm wrong and actually the lottery number really determines the closing price of the stock market, then maybe my model is wrong. But it seems reasonable to model X and Y here as kind of independent quantities. Okay. Okay, so these are things that are independent. Of course, not everything is independent. So there's things that are not independent. So one common example is if you reuse a sample. So if I let X be the result of a fair coin flip, and then I let Y be the result of the same coin flip, so Y is equal to X, then kind of I hope you believe that X and Y are not going to be probabilistic independent. Kind of if you observe the value of X, it's going to tell you exactly what the value of Y is. Okay, and if you observe the value of Y, it will tell you exactly what the value of X is. You could kind of think of other examples where maybe Y is the negated version of X. And again, in this case, since they come from the same source of randomness, X and Y are not going to be independent. So continuing on the previous example, again, some things that you would like to model probabilistically should not be modeled as independent, right? So these are often things that have what we believe to be a common cause. So if I think of X as today's kind of ice cream sales, and then Y as today's kind of sunglasses sales, then it makes sense that maybe X and Y are not going to be independent because they're not really uncorrelated, right? So if the temperature is higher, maybe I expect both X and Y to be higher because people, eat more ice cream and they maybe buy more sunglasses when it's warmer. And when the temperature is very low, maybe people don't want to eat ice cream or buy sunglasses, so they're both going to be low. Okay, so this is an example, a simple example of when you might want to model two things as not independent. Okay, great. So speaking a bit more formally, what is independence? So again, if you've seen these definitions before, this is probably not very surprising. But as a quick review, suppose that we have two random variables, X and Y. We say they're independent in some implicit distribution over X and Y. So there's always some distribution over X and Y that's in the background, even if we don't name it. X and Y are independent if for all values A and B, we have this kind of equality here, which I'm trying to highlight here, but this equality here. So essentially the probability of seeing X equals A and Y equals B is equal to the probability of seeing X equals A times the probability of seeing Y equals B. So intuitively, this means that the distribution over X and Y is a product distribution. So it's the product of a distribution over X and a product of a distribution over Y. So a product of these two so-called marginal distributions. If you haven't seen this definition before, you might not understand, why this is a reasonable notion of independence. But this turns out to be a very useful notion.
Hey, Justin.
Yes.
So there's one comment from Dexter.
Yes.
Saying that this definition holds for discrete distributions only.
Yes. Yes. So that's a good point. So everything I'm talking about today will be for discrete distributions. I'm sticking with actually even finite distributions. So say A and B are Boolean, let's say, just to keep things simple. Of course, this can be all generalized to continuous distributions, but I won't be doing that here.
Great. Yeah. Thanks.
Mm-hmm. Any other questions?
I'm not seeing any other questions.
Okay, great. Okay, so why is independence useful for program reasoning? The perspective we're taking in kind of this talk is that we want to use independence as a tool for reasoning about probabilistic programs. So I would argue the first reason that this is a useful idea or useful concept is that it's ubiquitous in probabilistic programs. So kind of, the basic command of generating a fresh random sample, which is kind of present in all probabilistic programs, is somehow described by saying a fresh random sample is independent of the rest of the state, right? So I have a bunch of variables already, which might be randomized, and I generate a fresh one. What makes it fresh is that it's independent of everything I already had before. Okay, so it's very useful to be able to capture this kind of property for such a basic construct like random sampling. The second reason I think independence is very useful for reasoning is not just for program reasoning, but also applies just as well to proofs on paper, is that it simplifies reasoning about groups of variables. So quite often in many probabilistic programs or randomized algorithms, we're working with not just a single random variable, but a collection of random variables, right? So I might have maybe an array of n kind of random coin flips, and I'm going to do something with these things. So in general, reasoning about distributions over groups of variables is tricky because there's many possible values of these variables, right? So if I have, say, n kind of coin flips, there's kind of 2 to the n possible realizations of these coin flips. And if I had to kind of track the probability of each specific realization, kind of in the worst case, in the most general case, I might need to track 2 to the n separate numbers. Okay, and this gets really, really complicated. Even if n is like fixed, you don't want to be tracking all of these probabilities. So in general, kind of maintaining the general distribution over many variables, kind of tracking these different probabilities is very complex. However, if we know that all of the variables, or at least many of the variables, are independent, then the task is much simpler, right? So I can represent this distribution over a product as a product of distributions over each variable. So I can factorize my joint distribution into a bunch of simpler distributions. This is very nice because often it's much easier to kind of say, okay, this single variable is uniform, or that single variable is, you know, a biased coin flip, rather than trying to describe the joint distribution of a bunch of variables at the same time. So having independence available makes us able to represent complex distributions in a very compact and precise form. Okay, so the last reason I would argue why independence is useful for program reasoning is that this is a property that's preserved in many common program operations. So kind of like I briefly sketched before, like kind of local operations that operate on independent or separate randomness preserve independence. So if you have independence at the beginning of your program or at the start of your sampling, which again is quite common because a fresh random sample is going to be independent, this kind of independence property is often preserved for much of your program because you're operating on separate randomness, and then the independence will be preserved. You're operating locally somehow. Another reason why independence is useful for probabilistic programs is that it behaves well under conditioning. So we might see this a bit later when I'm talking about kind of probabilistic control flow. That one of the typical ways of modeling kind of randomized branching or randomized loops is by conditioning. So you might condition on the fact that the guard of the program, guard of the conditional is true, and that is going to affect your distribution, your input distribution. So in general, it might change your input distribution in kind of very strange or unpredictable ways. But if you know that certain things are independent, then you know that parts of your program state will kind of not be affected once you condition. And this is, again, very useful for reasoning in the presence of this kind of probabilistic control flow. All right, so I hope you're kind of convinced that independence is a very nice concept. It's typically not the final thing you want to prove for your probabilistic program, but it's very useful for kind of intermediate reasoning in your program. All right. So let me talk a little about the challenges about reasoning about this property. It's a very basic property, but it doesn't seem very amenable to like direct verification. The main reason I would say is that the formal definition doesn't look very promising. So first of all, there's this quantification over all values. So I showed a very simple example where you have kind of 2 Boolean variables, but in general, you might have kind of variables over larger supports, or you might have more than 2 variables. And this kind of quantification over all values seems to involve a lot of probabilities. Furthermore, computing exact probabilities of probabilistic programs is often difficult. It's often intractable. We really don't want to be computing kind of all of these probabilities and multiplying them together, one by one. That is generally not going to work. Even if it does work, it's going to be very, very tedious. So kind of what we want to do is we want to try to leverage the intuition behind probabilistic independence. So if you talk to people who kind of think about randomized algorithms, they don't spend all day kind of computing all of these probabilities to show that stuff is independent. They reason got kind of a more high level perspective where they say that these things are from separate randomness, or these things are transformed in a certain way, and therefore we don't actually need to kind of do the computation to show that they're independent. We just know that they are. So we want to kind of leverage this intuition behind independence to develop program logic or some logical reasoning tools that can talk about independence in this kind of more abstract way. Okay. So the main kind of observation of this talk is that one way of viewing independence is as a kind of separation. So I'm not going to say this is the only way of viewing independence because, of course, it's not good for everything. But I think a very fruitful way of viewing independence is as this kind of separation. So we'll think of 2 variables, x and y, in a distribution. I'll call mu, are independent if mu is a product of two distributions, I'll call mu x and mu y, with disjoint domains. And mu x's domain contains x, and mu y's domain contains y. Okay, so here we really emphasize that it's a product distribution, and it's over some disjoint domains. So this observation doesn't seem very different from what I just presented, but enables us to kind of leverage tools from separation logic to reason about independence. So this is a very well-developed area of program verification research that is continuing today. So it's pioneered by O'Hearn, Reynolds, and Yang, and many other people. There's a rich logical theory. People have investigated automated tools, and there's many kind of nice results or techniques known in this area that we can try to bring to bear in the probabilistic setting now. So kind of what I want to talk about today are kind of the two main ingredients for our approach. So we kind of develop a probabilistic model of the logic BI, which I'll talk about more. That's the first part. The second part is that we design a probabilistic separation logic, which we call PSL. So this is a kind of a program logic or a Hoare style logic, which can let us reason about independence for probabilistic programs. Kind of before I talk about these two things, I'm going to talk more, kind of give a background on both BI and separation logic for people that are not familiar with this, but then we'll talk more about these two things. Okay, any questions before I dive into this? Okay. So I'm going to do a quick recap on bunch implications, or this logic BI and separation logics.
Sorry, Justin, there are
yes.
a couple of questions, I think.
Okay, sorry, I can't see the questions.
One from Dexter. So
okay.
I am unmuting Dexter. So.
Hi, Justin. On your previous slide, you said something about X, the disjoint domains containing X and Y. What does it mean for a domain to contain X? What do you mean by contain?
Sure, that's a good question. So I'm thinking about mu and, I'll talk about this a bit more in a second, but I'm thinking about mu x and mu y as being distributions over memories. So let's think about a memory as a map from some domain, which is some subset of variables, say finite, to values. And so I have mu x is a distribution over memories. And these memories all have domain containing x. And mu y is
what is it? X is a random variable, right?
So I'm treating x as just a name, let's say.
Yeah,
like
but what does it mean? Then what does it mean for a domain to contain X? I don't know what that means.
So I'm thinking about mu x as a distribution over maps from a set of variables to values. So the fact that the domain contains x means that this set of variables contains x. So maybe it will help if I actually write this. Let me quickly grab.
I don't think I'm with your definition.
Let me see. Let me grab the chat. So I think of mu x, let's say mem s is defined to be s to val. S is
are we supposed to be seeing what you're typing?
I'm trying to send a message.
Oh, I see. Okay.
S to val, where S is a subset of. Can everyone see that in the chat?
Yep.
So then mu x is type a distribution over mem s, where x is s. So here I'm thinking about the set of variables I call v and the set of values val as some fixed sets.
Okay. Okay, gotcha.
Okay?
Yep.
It's a good question. I'm going to define this more later, but at this early stage, it's undefined.
Okay.
And Jamie also has a question.
Okay.
Oh, okay. Thanks, Coco. Yeah, thanks, Justin. So my question is, so I don't work in this area, but before you give the formal logic, I would really benefit to hear an example of the sort of I guess, the sort of verification problem you would like to solve, but you currently can't without a better understanding of the logical structure of uncorrelated variables. It's clear that if you can, I mean, it's clear that this is a nice thing to do, but can you give a compelling example of some probabilistic program that you can't analyze efficiently at the moment without these techniques, just as a motivation before we go into the logic?
Sure. So I'm not going to show an example at this point because I think it's a bit early and I would need to introduce more notation. But the main examples that we were working with in this paper come from the domain of cryptography, where we'd like to show some cryptographic security property. So I can outline this at kind of a high level right now. So let's suppose that you have some encryption routine, which takes in some secret message and produces an encrypted output by adding some randomness or doing some transformations. So naturally, we like to say that the encrypted output perhaps doesn't reveal any information about the unencrypted message. So there's different ways you can model this kind of property. You can model as kind of a two property or things like this. But one natural way is to say that the encrypted output is probabilistically independent of the input. So viewing the kind of secret input as drawn from some distribution that you may not know, whatever we do with this input is going to lead to something that is independent of the input.
So you're saying that the security property, as part of the specification, is an uncorrelatedness, is an independence property. So to have that in the logic, I mean, seems useful.
Right. So that's one way of doing the security property. There's different ways of encoding this kind of security property. I would say more though that I'm not claiming that none of this stuff can be verified without thinking about independence. I'm only claiming that using independence leads to easier verification and allows you to compute or kind of verify stuff at a higher level without computing a ton of probabilities. I think there are always ways to kind of reason about these programs in kind of a messier or more complicated way if you're willing to do a lot more computations, but independence can simplify the reasoning.
Okay, thanks. That's exactly the sort of overview I was hoping for. Thank you.
Great. Are there other questions?
I think that's it.
Okay, sounds good. All right. So before I kind of get to the problems of separation logic, I want to give some background on a bunch of applications in separation logics in general, just to see kind of where we're coming from and kind of our plan going forward. So kind of what goes into separation logic? Kind of from my kind of opinionated perspective, there are kind of three main ingredients. So first, there are programs. Okay, so there's some way to transform input states to output states. Typically, these are imperative programs, but people have to develop separation logics for functional programs and other settings as well. So you need some class of programs and some semantics of these programs that transforms inputs to outputs, let's say. The second thing that you need is a class of assertions. So these assertions are formulas that describe program states, or maybe more generally, kind of fragments of program states. Almost always, this assertion logic is kind of drawn from the logic BI, a bunch of applications by Pim and O'Hearn. And so you need semantics defined by a model of BI. So you need to have a semantic saying, which formulas in BI are true or are valid at which program states. So for you need programs and you need assertions about program states. And the final thing is you need the program logic itself. This is a Hoare style logic where the formulas are describing programs, not program states. So this is a typical kind of program logic where you have a precondition and a postcondition, and these assertions are drawn from the assertion logic. And these assertions let you talk about, pre and post conditions of a program. Okay, so these are kind of the three things that I think go into a design of kind of any separation logic. And when we design our probabilistic separation logic, we're also going to kind of follow this template. So when we talk about separation logic, maybe the simplest setting is the heap setting. So in this setting, program states are pairs of a store and a heap. So a store, which I'm writing S, is a map from a set X of, this is a finite or fixed set of variables, to V, which are values. This is a total map. So this idea is you have some finite number of variables or some fixed set of variables, let's say, that your program can use. And then along with the store, there's a heap, right? So a heap H is a map from natural numbers to values, and this is a partial map. So this represents you have some memory that initially is mostly unallocated, maybe all unallocated. And at certain cells in your heap, you may kind of store a value or access or read or write a value. Okay. And then the programs in classical separation logic are heap manipulating programs. So you have the typical control flow like sequencing, if then else loops. You have additional constructs that allow you to read and write addresses in heaps or allocate or free heap cells. Okay. So on top of this, the assertion logic, at least in classical separation logic, is a logic bunch implications. So this is substructural logic where you start with a regular propositional logic with your regular connectives that you're all used to. You add a new conjunction called star. So you can have a formula P star Q. And you add a new implication called magic wand, which is a joint to the conjunction. So P magic wand Q. So the idea is that star is a multiplicative conjunction. So P and Q means that P and Q both hold on the entire state, entire program state, let's say. P star Q means that P and Q hold on disjoint parts of the entire state. So they don't both hold on the entire thing, but you can split the state into two disjoint parts where P holds on the first part and Q holds on the second part. Okay. So now to give a semantics of these logical formulas in program states, we're going to use what's called the resource semantics of BI. This is a very general semantics that is also quite intuitive. So kind of the main thing we assume is that the set of states S is pre-ordered and that there's a partial operation on S, a partial binary operation S, which is associative and commutative in a certain sense. Once we have this structure, we can then define the semantics of all of the logical formulas.
Justine, there's another question from Jamie.
Yes.
Hi.
Hello.
Oh, yeah, I remember you said, okay. Could you go back to the previous slide quickly?
Yes.
Are these partially defined, these conjunctions, or totally defined?
So you can certainly have this conjunction. I mean, grammatically, you can form the conjunction for any two formulas, but clearly, because for instance, for a star, like P star P is usually not going to hold because you maybe are not able to split the entire state into two disjoint parts where P holds on both parts. So does that sort of answer your question?
So the assertion is defined, but it may not be satisfied.
Yes.
Okay.
Okay. Okay, so we can inductively define, which formulas are true on which states. So some of these are kind of obvious. So kind of the true formula is always true or is always valid in any state S. The false formula is never valid in any state S. P and Q is going to be valid in state S exactly when P is valid in S and Q is valid in S. But the more interesting cases are for kind of the separating conjunction, where you have kind of definition that looks something like this. So this last highlight definition, I'm saying that P star Q holds in S if I can find S1 and S2 also state, kind of such that when I combine S1 and S2, the combination is defined and kind of less than S or contained in S, and P holds on S1 and Q holds on S2. Okay, so this reading kind of looks like you're kind of combining two things, but I like to think about this as saying that the state S can be split into two disjoint states or two compatible states, and the first state satisfies P and the second state satisfies Q. Okay. Any questions about this? So far we're still in kind of standard BI, but we're going to be using the semantics to define our interpretation for probabilistic formulas as well. Okay. So as another example of this setup, we can return to this classical heap model of BI, where the set of states is going to be heaps. So S is going to be partial maps from natural numbers to a set of values. So think about these natural numbers as addresses, like memory addresses. And the monoid operation allows you to combine two disjoint heaps. So S1 combined with S2 is defined to be kind of heap union, kind of union of partial maps. if and only if the two heaps have disjoint domains. So if the domain of S1 and domain of S2 have no intersection, they're disjoint, then we can combine them together. So again, a domain of S1 and S2 are kind of the set of addresses where the map S1 or S2 is defined. And the preorder allows us to relate two heaps by extending or projecting. So S1 is less than S2 exactly when the domain of the first heap is less than the domain of the second heap, or contained in the domain of the second heap. And both heaps, S1 and S2, agree on their common domain. So intuitively, you could think about this as saying that S2 maybe has more information than S1, or S1 is a subheap of S2. Okay. Questions about these examples? Okay, so the last few things we need to kind of complete our treatment of kind of this heap model of BI is that we need this kind of atomic propositions to talk about heaps. So in separation logic, as presented by Hernan, Reynolds, and Yang, you have this atomic proposition called points to, where we say X points to V, holds in some heap S, exactly when X is in the domain of S and S of X is equal to V. So this is holds in a heap if the kind of the address you could think of as of X is allocated, and the heap at address X contains the value V. And along with this, you can have some example axioms. Of course, these axioms are not complete, but they're useful already for a lot of program reasoning. I won't go over these too much here. They're mostly fairly intuitive. Okay, so finally we get to kind of the separation logic proper. So this is kind of the program logic itself. This is the kind of, remember my three-step thing where you first have programs. The second thing is you have assertions about program states. And now we're at kind of the program logic where you combine these two things together. In the separation logic, the programs C come from a basic imperative language. I'm going to add kind of two constructs here for reading from a location and writing to a location. So this is kind of like pointer dereferencing. So here I'm saying, I have a variable X. I want to read from location given by E and store the result into X. The right is kind of the opposite, where I have some location that's represented by E, and I want to write to the value, write to that address. I want to write to the address that new value, E prime. And so you can think about E here as like a pointer, something where you're dereferencing and reading or writing to that location on the heap. And then the program logic judgments are now straightforward. So they look exactly like Hoare-style judgments. You have P and Q are the precondition and postcondition. C is the program from your basic imperative language. And kind of the reading of this or the validity of this means that kind of executing C on any input state satisfying P leads to an output state satisfying Q without invalid reads or writes. So kind of if you try to do something here where you kind of read to a location that's not allocated or write to a location that isn't allocated, then the semantics of the program is going to kind of result in some error state. And this judgment being valid in regular separation logic means that this kind of runtime error is not possible. So your program has no memory errors in some sense. Okay, any questions about this?
It seems there's no question.
Okay, so I'll show some proof rules really quickly. These proof rules will also be used kind of in different form for our separation logic. For reading and writing a location, here's a rule for reads. So we say that if X initially points to V, and then I execute a command that kind of dereferences X and stores a result in Y, then I'm going to end up in a state where X points to V and Y is equal to V. So here I'm thinking about Y as kind of a variable in the stack. So I'm reading something from the variable, from the location X. Initially it contains V, so I'm copying V kind of to the variable Y. Okay, so this is the rule for reads. The rule for writes is very similar. Initially, maybe X is pointing to V. Kind of X is some address, and in the heap, this address is allocated and it holds V. Now, if I write a new value E or new expression E to this location, I'm going to end up in a state where X is going to point to E. Okay. Actually, this V here doesn't really matter. What really matters is that initially X is pointing to something, that X is in the domain of the input heap. And that allows me to write to that location without incurring a memory error. Because if it wasn't in input heap, then I'm not allowed to write to that location. Okay, So the last thing I want to show about this kind of standard separation logic is the frame rule. So this is a very well-known rule from separation logic, and intuitively states that properties about unmodified parts of the heap are preserved. So reading this rule, we can say that in the premise, you can prove that P and Q are pre and post conditions of C. And now we suppose that the program C does not modify the free variables of a formula R. So intuitively, R describes a portion of the heap that is not modified by C. Then we can conclude that P star R is a precondition. And if I run C there, then I will have Q star R. So as long as R is kind of describing a portion of the heap that is not is disjoint from the portion described from P, then I don't have to worry about whether R is still preserved or not after running C. Okay, so in some ways, this rule is maybe the most well-known rule for separation logic, and it leads to what's called so-called local reasoning in separation logic, where I only have to reason about the part of the heap that's used by C. The rest of the heap is automatically preserved, so I don't have to reason about that part when I'm doing my proof. It's also important to know that this really relies on the separating conjunction star. So it doesn't hold the star is replaced by regular conjunction due to aliasing, because you may have two variables that syntactically are different, but they refer to the same heap address. And then you might not know whether C is going to modify the heap location that another variable is actually aliased to as well. But if you have separating conjunction, then this cannot happen. Okay, so this is pretty much all I'm going to say about standard separation logic. Are there any questions?
I don't see any questions. And then I think we have like 10 to 15 minutes left.
Okay, I have to go faster. All right, so now let's get to our probabilistic model of BI. So the main idea is that instead of having states being memories or heaps, our states will be distributions over memory. So this gets back to Dexter's question. So I'm going to fix a set X of variables and a set V of values. For now, let's just say this set of values V is going to be the Booleans, so some finite set for simplicity. We're going to be working with memories that are indexed by domains. So what I mean by that is that I'm going to consider subsets of variables, say A as a subset of X, to be a domain of some memory. And I'm going to write M of A for maps from A to V. So these are you can imagine them as stores or memories where you're allowed to talk about the variables in A. This might not be all of the variables, but it's some subset of them. And then program states are going to be randomized memories. So states of distributions of memories with the same domain. So formally, each state is going to be some probability distribution over memories over some set A. So kind of written out here. And when some distribution S is inside kind of this set, we're going to write domain S to stand for A. So these are the variables that roughly we can talk about in this distribution over memories. Okay. So hopefully this setup is sort of clear. So I want to clarify here that we're not talking about heaps here. So we're not talking about some partial maps from addresses to values. I'm really fixing a set of variables and talking about distributions over memories of these variables. It's possible to actually extend, let's say, I believe it's possible to extend everything we're doing to also with heaps, but it seems like an orthogonal extension. We're focused here just on talking about disjointness as independence and not disjointness as kind of heap separation. Okay, so now to introduce our model, the basic idea is very simple. Kind of two distributions can be combined if their domains are disjoint. And in order to combine two of these distributions, we kind of take the product distribution and we kind of take the union of their domains. Okay, so a bit more formally, suppose that S is a distribution over memories over A. That's the first thing. And S prime is a distribution over memories over B. So A and B are both subsets of variables. Now, if A and B happen to be disjoint, then I can define this combination where I say S combined with S prime, evaluated at kind of a memory, M union M prime, is equal to the product of these two things. So the kind of this, you can read this as the probability of seeing M union M prime in the combination is equal to the product of the probability of seeing M in S and M prime in S prime. Okay, so you hear this is just regular multiplication. Otherwise, if A and B are not disjoint, kind of what we say, the domains of S and domain of S prime, if they're not disjoint, then S combined with S prime is undefined. So you're not allowed to combine two distributions that both talk about some common set of variables. Okay. Is this definition clear? Okay. Now, the preorder we can define in a very natural way. Again, I'm going to read S is less than S prime as saying S has less information than S prime. So in the probabilistic setting, we can think of as S being a projection of S prime. So you get a projection or a marginalization. So idea is that, again, we have S and S prime being distributions over memories of A and memories of B. Then if A is kind of contained in B, which means that kind of S prime is a distribution over memories over more variables, then if we marginalize S prime and remove all the extra variables, we get the smaller distribution S. So this is, again, kind of a standard operation for distributions over products. So we're really working with our distributions over products. And this says that we can marginalize the bigger distribution into the smaller distribution. And that's when S is less than S prime. Okay. So kind of what I've talked about here is enough to kind of already define a model of BI. So we can extend the semantics that I presented before, the standard semantics that has been well known. That one will give us a model to talk about, when is P star Q true in a distribution of memories, when is P and Q true in a distribution of memories, and so on. And so all of that works exactly as standard. The main thing we also need is kind of the analog of these points to predicates, right? So we need to have some way to talk about distributions. And here's where we need something specific to distributions. So I'm going to use some atomic formulas to talk about distribution. So I'll say E is equal to E prime, holds in distribution. If E is always equal to E prime, with probability 1 in the distribution. And of course, all the variables mentioned by E and E prime must be in the domain of S. So you must be working with a distribution over memories that all have enough variables to talk about E and E prime, where E and E prime makes sense. These are two program expressions, let's say. We'll also be working, we usually have kind of distribution laws where we'll say maybe E is distributed as a uniform distribution. Again, this only makes sense if you're in a distribution where the free variables of E are contained in the domain. And furthermore, E should be uniformly distributed, say as a fair coin flip, if we're sticking with just Booleans. I'll write this formula like E is distributed as D to say that E is distributed as some unknown distribution. The only thing I know is that all of the variables inside E are contained or kind of defined in my distribution over memories. Okay. All right. So again, we can have example axioms. Mostly go through these fairly quickly because I'm running out of time. The only one I'm going to highlight is kind of these last two here, because maybe they're more interesting. So this one here lets us kind of say if X is uniform and Y is uniform, and they're both independent, then the pair X comma Y is also uniform over pairs of Booleans. Okay, so this crucially relies on independence here. It is not true or it's not valid if I don't have a separating conjunction here. Likewise, we can have other kind of axioms that relate uniformly to kind of exclusive OR. So this one says that if X is uniform and independently Y is distributed to some other distribution, but it's independent, and Z is equal to X exclusive OR Y, then Z is uniform and Z is also independent of Y. Okay. Of course, none of these are complete, but again, these are useful for verifying small programs already. I think I'm going to skip over this discussion here in the interest of time. And I just want to give a brief sense of the probability separation logic. So we're going to be working with a kind of probabilistic programming language. Here, I'm taking out most of the features. I'll have just the simplest features. I'm taking out loops, though we have a way to treat loops as well. The main new construct we have is this random sampling command, where I sample something from a uniform distribution and I store it inside X. So you can think about this as a fair coin flip. Say this is uniform over the Booleans. And the semantics, we take the standard semantics as distribution transformers due to Cozen, where a program transforms a distribution over memories to another distribution of memories. So in our very simplified language, There's not even non-termination, so it's really a proper distribution to another proper distribution. Then we can kind of use our atomic formulas and our, the probabilistic version of BI as assertions to talk about probabilistic programs. So again, the reading of this is entirely standard. The one thing I would point out is that we're kind of quantifying over all states that are distributions over all memories. That would be the only thing that is maybe a little bit different from regular separation logic, where you might talk about states that don't mention all of the heap cells or all of the possible memory locations. Okay. So I want to give a sense of some of the brief basic proof rules in PSL. So this one is kind of, I'll present just the forward rules. For assignment, initially, if we just have true, and I store E and X, then I'll get X equal to E. For sampling, it's very similar. Initially I have the true precondition, and I sample a value and store an X, and I'll get X is distributed as uniform. Conditional rule, I think, let me see. Okay, I'll mention briefly the conditional rule because it's one of the more interesting parts of the logic. It looks very different from the regular conditional rule, and that's because we have to deal with certain other things in a probabilistic setting. So I'll first remark that the preconditions here, which are P, the precondition P must be independent of the guard. So that's reflected in the precondition, where E distributed is independent of P. And this is because in order for this input distribution, when we go to the branches, we have to condition on the guard being true or condition on the guard being false. So in general, we don't actually know if P is going to hold unless we know a priori that it's going to be independent of the guard. So if it is independent of the guard, then I can preserve P as a precondition to the branches. So this is one crucial place where we're using independence to preserve some information about the precondition, otherwise we would not have. Second point is that Q, the postconditions, first of all, must be the same, and they must be the same Q, and they must also satisfy this additional syntactic condition called supportedness. And this is because not all postconditions Q can be soundly combined together like this. Essentially, Q being supported means that Q describes a unique distribution. So this is a standard concept from separation logic. And it's needed for technical reasons to ensure that Q is kind of preserved when we take convex combination of distributions to kind of union the two branches, the result of the two branches. Okay. Our frame rule is looking a little bit more complicated than in regular separation logic. I think for lack of time, I'll not talk about this too much, but we do have a frame rule, and that's what I'm going to say. And given kind of the frame rule and the sampling rule, we can define this kind of global version of the sampling rule, where the precondition R can be any formula, and it's preserved kind of to the postcondition, capturing intuition that when I do random sampling, the result I get is going to be independent of everything else in the program state. Okay. Okay. I'll skip this part as well. So, see, I think I'm probably nearly out of time because I planned this rather badly. I could talk about Coco. How much time should I stop right now, or should I continue and try to do an example really quickly?
I think we all want to see some examples, so let's say.
Okay, let me do an example really quickly, just to see how this logic is used, and I can conclude there. So the example I'm going to do is this kind of example from cryptography, which is maybe the simplest encryption scheme possible, called the one-time pad. So you have a program where the input is a message M, and it's let's say it's a Boolean for simplicity. And the output is a ciphertext C, which is also a Boolean. Of course, this can be generalized to much more complicated or a string of bits. And the basic idea is that you encrypt by simply taking an exclusive OR of the message M with a uniformly random key K. So the encoding program is just 2 lines. This may be the simplest example we can give, where we sample the key uniformly and then we compute the exclusive OR. And C is going to be the output, which is going to be the ciphertext, the scrambled version of the message. So like I mentioned, there are several ways of formalizing security. The first way is just showing that C is uniformly distributed. So that means that the distribution of C is always going to be the same no matter what the message M is. The second method is the one we're going to actually use. We can use both of these things, but I'll show the second one, where we have this input-output independence that I mentioned to Jamie, where We assume that M is drawn from some unknown distribution, and then we're going to show that C and N are independent in the output, which means that observing C will give you no information about the secret message M. Okay, so I'll briefly sketch the proof here in PSL. So here's our program here, this 2-line program. The assumption is that M is drawn from some distribution that we don't know. It's any distribution. By using the global version of the sampling rule, the last one I quickly derived, we can show that K is going to be uniform and it's also independent of M, okay? Because it's a fresh random sample. By using a global version of the assignment rule, which I didn't have time to show, we can then show that after assigning Kx or M to C, we have this other conjunction, C is equal to Kx or M. And then finally, we can conclude by using this XOR axiom that I briefly mentioned, where we can conclude that C is uniform and C is independent of M. And this is kind of what we wanted to show. Okay, so this is a very quick sketch of an example that we've done in this logic PSL. We've done more complicated examples like oblivious transfer, verified security. We've verified a simplified version of oblivious RAM as well using this program logic, which unfortunately won't have time to show here. But okay, maybe I'll just jump to the very end. You should look at the papers for more details. So we have many more examples in this paper, probabilistic separation logic. We have many extensions like adding deterministic variables, adding loops, and things like this. And if you follow this talk, I think it should be pretty approachable. What I didn't have to talk about is more recent work where we try to extend these ideas to conditional independence and develop a new bunch logic called DIBI for dependence and independence bunch applications. And there's much more to talk about there as well, but I'll stop here.
Thank you, Justin. So I will unmute everyone so that we can have a clap. Is it working? Yes. So thank you, Justin.
Thanks a lot.
Actually, you finished the example in 3 minutes, so we have quite a few minutes for questions. Okay, Jamie has one question.
Okay.
Yeah, hi Justin. Thanks for a really nice talk. So my question is about quantum computation. I wonder if you thought about the extension of these ideas to quantum computation rather than probabilistic computation. In particular, a very close analog in the quantum world to one-time pad encryption is quantum teleportation. The structure is almost identical. Indeed, the correctness criterion of the quantum teleportation algorithm is exactly an independence, there's a sort of quantum statistical independence property of the final quantum distribution.
Right. So I have thought about this a little bit. Like I've been talking with some collaborators about a quantum version of the separation logic, where kind of separation kind of models some kind of separated quantum states that are not entangled somehow. I'm not quite sure whether I can kind of present like an example of that, but I believe there is something to be done there. And many of these ideas are likely to be useful also in that setting. But that's pretty much all I can say right now, I think.
Great, interesting. Maybe we could talk more about that. Very interesting.
And Dexter has a question.
Okay.
No, I'm all set. Thanks. Just wanted to thank Justin for a nice talk. My question's been answered. Thanks.
Thanks.
Right. And then Ruben has a question.
Hi, Justin. Thank you for the talk. I hope these are simple questions. Do you have examples where the guard of the conditional is not independent from the precondition that you would want?
Right.
And then another question is, can you extend this to handle loops?
Right. So those are both good questions. So your first question was, are there examples where the guard is not independent of the precondition that we would want or that we can support?
Well, I guess examples where I guess where it's necessarily the case that the that the guard is not independent? I mean, where you, so that you wouldn't be able to handle currently in your logic, but
right. So you're right that the conditional rule that I showed does require that the guard is independent of the precondition. So this is part of the motivation for kind of more recent work on trying to capture conditional dependencies and conditional independencies. In logic, we're able to lift some of these restrictions and allow the precondition to kind of depend on the guard and still kind of continue reasoning in that way. Now, I should say that the frame rule inside PSL already partially compensates for this kind of limitation, where kind of you're still able to frame things through that maybe you can't use as a precondition, but if you know it's not modified, then you're still allowed to kind of frame it through. So you're not everything is lost if you don't know that something is independent of the guard. But this is definitely a limitation of the logic. Your second question about loops is also good. So what I didn't show is kind of the full version of the separation logic where we have deterministic variables and we have more constructs. So it turns out that for reasoning about deterministic control flow, many things are much easier. So kind of this restriction on kind of the guard being independent of the precondition, you no longer need this restriction anymore if you know the guard is deterministic, because intuitively the deterministic guard is independent of everything else. So we are able to kind of give loops where the guard is deterministic and conditionals where the guard is deterministic as well. For loops where the guard is randomized, things seem much trickier. Kind of even if you assume, or kind of as assumed as a side condition, that the loop is terminating, infinitely many steps or in a bounded number of iterations, or with probability 1 or whatever, it seems difficult to kind of think about independence, things that might come out. So kind of believe that probably if the guard is independent of the loop invariant and you have termination, then such a loop rule would be okay. But we have not worked out the details, and there's kind of few examples of that, I think. Kind of in many of the examples that we have, kind of it's enough to use these kind of deterministic loops, and then the reasoning is much simpler. The proof rule is much stronger.
Okay, thanks. Yeah, that's really interesting. I'll have to go and read your paper.
Is there any question? We have a couple of minutes. Okay, I have a kind of naive question related to Ruben's one. So for the conditionals, there's this limitation for the precondition, so that it has to be independent from the guard. And then what about the post condition? There's also this independence thing. Is that also a limitation?
So let me pop back really quickly to the conditional rule again. Right, so this is the conditional rule again. Right, so the post condition is Q, so I can talk about this a bit more. Here, in the post condition here, in the branches, this is not really a restriction, because essentially we're essentially saying that the guard cannot be changed during the execution of the program, of the branches. Like you fix E to be equal to true initially, and since it's deterministic, you're assuming kind of it's independent of P. Then you run C, and then you again have E is true, kind of with probability 1, and it is independent of the post condition Q. So this independence here is usually not a strong requirement. The bigger requirement is definitely the supported condition, which I didn't have time to kind of define fully. Essentially, Q being supported means that Q is true in a unique distribution. So an example of a supported assertion is saying that maybe some variable Y is uniformly distributed, because you know that if Y is uniformly distributed, then it picks out one exact distribution. So an example of something that's not supported is if you said Y is distributed as some distribution, like Y tilde D. That is not a support assertion, because there might be multiple different distributions that satisfy that assertion. But if you notice Y is uniform, there's kind of only one distribution. Like if you restrict, and there's only one distribution that satisfies that. And kind of what's happening here is that in these two post conditions, the post states, in order to kind of combine them together to give a post state of the whole conditional, the one satisfying this thing, we need to take a convex combination of two distributions. One is satisfying the first thing, and one is satisfying the second thing. And we need to ensure that kind of whatever is true, we want to ensure that Q is kind of preserved on this kind of convex combination. And this is true for some assertions, but not for other assertions. But a sufficient condition is that Q is supported. You know, if Y is uniform in two distributions, and I do a convex combination of the things, then Y is still going to be uniform.
I see.
Yeah.
I see. Thanks.
But they're difficulties for both the precondition and the postcondition for the conditional rule. Both splitting apart, we need independence, and for combining, we need this supported condition.
Right. Thank you. So if there's no further questions, then we can stop here. So you can all unmute yourselves, and then we will thank Justin again. Thank you.
Thanks, everyone.
So that's the end of the talk, and then we will have the coffee break afterwards. So if you don't want to participate, then I recommend you leave now. And then if you'd like, then you can stay here with your video and audio on, and then I will assign you to randomly to breakout rooms.
Good.
Let's see how many are we. There's a possibility that we don't need to actually split.
one big coffee break.
Yeah, you deserve. So we're 11 right now.
That's a good number.
Yeah. So I actually think we don't need to split.
Can you stop the recording, Coco?
Surely. Yes. Did it stop? No.